Alright. Hey everybody, back with part 2 of this Defender board set repair series. I don't know, this is the arcade buffets. This is a quick intro. Right after part 1, I come right into this part 2, and we'll be right back with the start. And the original PIA, the arcade buffets, or the one that came with the board. And this is his CPU board, his interface board, which I haven't tested yet. His soundboard, which had a blown fuse, replaced it, seems to be working. ROM board, placed the ribbon cable, that's all I had to do. And let's see if this thing works. Oh, it was missing RAM, right? So, damn, that RAM doesn't even seem like it's in there. Let me make sure all this RAM's in there. And all facing the right direction. Yeah. Alright, let's see. Nope. Solid. That's bad. We probably have a CPU. Let me try just swapping out the CPU real fast. Otherwise, we'll hook it back up on the... Alright, I have the Cat Box FPGA hooked up. Turned it on. We will hit open and turn on our power to our board, and we get no clock detected. And so that is, I wasn't thinking that was going to be the issue. I didn't even take the time to probe the clock signal, but I will now, and I bet we have a clock problem. So that's what I'm going to check next. Alright, have to break out the schematic because I don't remember everything, obviously off the top of my head, but basically find my clock circuit, my crystal here. You can check, you know, that it has 12 megahertz, and then that 12 megahertz gets broken into a 6 megahertz, gets halved basically by a 74, or a factor of 2 or something, I don't know, whatever. Different. Then we get 4 megahertz over here by 6R, and then that 4 megahertz comes into another 74, which gets halved again into 2 megahertz, and then into basically a Q as well as an E for our 6809 timing. So one is like kind of a inversion of the other, I'm pretty sure. So you got, you know, Q, and then you have E. This is, you know, not E and Q and not Q probably. So let's look at 7L7474. Make sure we get 4 megahertz coming in pin 11. See if that gets 2 megahertz out pin 8 and 9. Then we should see that come in at, you know, pin 3. And should be halved and be 1 megahertz at 5 and 6. There's my little notes right there. So we're doing 7L pin 11, 7L right here, 8, 9, 10, 11. Look at my oscilloscope. I move things around a little bit. 4 megahertz. All right, and then we're going to come to pin 8 and 9. Let's just come to pin 8. We got 2 megahertz. That's correct. Alright, and then that should go to pin 3, I believe. 1, 2, 3. 2 megahertz. And then that goes out 5. Oh, that's not right. It should be 1 megahertz. 5 and 6. And that doesn't look good either. But if I come to a chip that looks like it was replaced, which was 7J, pin 5 and 6, there's pin 6, we have our correct 1 megahertz. So I'm pretty confident. I'm not even going to break out my logic comparator. I think this chip is bad. We're going to replace the 7474 at 7L. Okay, got that replaced, that 7474. And we have a good 1 megahertz clock now. So let me go ahead and get my cat box back up and running. We'll test the RAM real quick, see if that works, and then go from there. I have my setup here for my RAM. Start the obviously that hit some address that triggered a sound. But our RAM test is failing, except for maybe part of the CMOS RAM test. So these are the different banks. One, bank 1, bank 2, bank 3, and then I don't really know how they have this set up with the. Let me see. If I go to setup, locations high to low, XX and 1E. I don't know if XX exists. I think I don't know how they did that. Note: enable and disable will write to given data to the specified before. Oh, enable before test. Yeah, so there. I don't know what the enable is. I guess there's no. Oh, it does say enable. D000 for the CMOS. That's the enable address. Enable. I guess we don't disable it after the test. That's kind of weird, right? It's the same enable address. I don't know. I have to go watch the video, I think, of that Fred did. If we do a ROM test, we got problems going on there too. Oh, that time it ran. Fine. Interesting, it failed before. So I got some learning to do on the FPGA, but we could also do some signature testing. I have to do some research on how they set this up to test the Fender boards. Alright, I've been playing around a little bit with the FPGA. So like any tool, you kind of have to learn when and how to use it. Just like if I was using signature analysis, or I'm using my scope, knowing what problem am I having, or if I was actually using my fluke over there, knowing what problem I'm having and kind of the best way to leverage the tool to give me a clue about what might be the problem. So it's kind of, sometimes you have to put in the effort to kind of figure out what's going on. But anyway, what I was doing is, well, the first thing I guess I was doing is I went to RAM test and I just disabled. Let's see if I can get this like this. Here we go. I was disabling all my RAM but one, and then running a 00 and then FF. So it's writing, all zeros to your, 8 data lines, and then it's going to write FF. So I think on pass 0 it's writing all zeros, and then on pass 2 it's writing FFF. So if we start the RAM test here, let me hit open. There we go. And RAM. Disable, disable, disable. I only want to test one bank basically. And we are going to do start RAM tests. And then it gives us the results over here on the bottom left. And it says, on address 0, basically, because I'm going 00 to BFF, so that's all we should be testing. So over here, I would expect it to go all the way to BFF. And it does. So it's testing all these addresses over here, and it's writing 00s and then FF. And you can see, like, there's no real pattern here. It's not like, that should be 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. There's no pattern. Like, I'm not always getting a 1 on one data line and always a 0 on another or anything like that. That's kind of what I was hoping to see with that test. So I'm like, okay, messed up data is going in, messed up data is coming out. That's kind of the conclusion I'm getting there. So from a signature analysis standpoint, we could check all the address buffers going to all the way through. I think it's a little bit different on Williams boards because they have 4 address buses they get combined and muxed together. Your pseudo address bus, your video address bus, your buffered address bus, and then I think there's video pseudo address bus. There's like 4 address buses that are getting muxed together and using the RAM. But what is kind of cool is there's a signature here for Defender that Fred or somebody already created who was using this thing. Alright, and it says here, force read write line to low, then check pin 2 of the DRAMs and pin 3, which is the write line, I guess, and then set the read write line over here to high and check pin 14. So we want to check it to low, and let's see, yeah, I have my gate right there, so I got my gate, it's going, and we're gonna come over here to our RAM and check pin 2. Okay, that's not good, is it? No. Let's see here if I can hold that. I might have to put this on. Okay, there's address line 1, and I am on basically pin 1 right here of the second RAM in the row. So it says A1, known signature A1, and then if I go to the next RAM chip, it says A2, which I think that's what I'm supposed to be seeing, like on the data in. But when I go to pin 3, which I assume should be low, it says it's high. That I just went to ground to verify that's low. If I come to a Yep, and I went to a TTL chip. As you can see here, I'm going to a TTL chip, reading, god darn it, TTL chip reading high, and that is high right there. So it's almost like that read-write line is not setting this up correctly. But anyway, so I think that's what you're supposed to do, and this RAM, it allows us to verify, and I'm not exactly sure what's going on, like basically taking the address counters, and it must be putting data, the address enabled, oh yeah, it says right there, enable data counter. So there's a data counter going on the data bus, so that when, I guess, I don't know, I'd have to have Fred maybe explain this, maybe he already did, I don't know, but when the address is like addressing the RAM, the data counter is putting the same data into the RAM, because he's like synchronizing the address counter as well as the data counter. And so what's being put in there with the address counter is being put in there with a data counter, so therefore you can read and write the same data in and out of the RAM and get the same signature that you would get when you were doing signature analysis on the address bus. I don't really know that for sure, but that's kind of like in the back of my head. But anyway, so then I was looking at it, and I know this is a long explanation here, but I was like, okay, let me do video analysis, because I did a whole signature analysis thing on my own Williams boards, like Joust, Robotron. I wrote a signatures analysis document and stuff. You don't really need that when you're using the FPGA CAT box, because it's kind of calculating the signatures for you automatically, which is really nice. But I was like, let me do that for this Prom, and they have the Prom at Prom 2, and I'm not even able to explain this correctly, but basically I was like, how the hell are they doing at 3C, the video decoder? How's he doing a signature analysis for that? And I realized that these Proms are in the wrong location. The video decoder is supposed to be up here, and the pseudo address decoder, I guess, is supposed to be down here. So these are swapped, and that might actually be my problem. And the only reason I figured that out is because I knew that trying to do signature analysis on the video decoder Prom, and is I'd have to move it's probably possible. I don't remember if I ever got it to work when I did signature analysis, but it's probably possible if I move my start, stop, and clock over to the video address counters. But I'm not going to do that because it's kind of, you know, pain. I'm just going to swap these and come my back. 2 proms, my 2 decoder proms there. We run our RAM test again. Up, and we're still getting failures. Alright, so I guess that's not our problem. Oh, well, I got one to pass. It just has nothing that has to do with the CMOS RAM. So that's good. I got one to pass, but all of these are bad for some reason. And it could be that read-write enable. Let me go back to signature analysis, load, RAM bank 1, DRAM bank 1, okay. Set that to low. I got my gate going. And if I come to pin 3, it should be low, right? Is that... But it's high. But my pin 2 looks good. I think that's good. I mean, it's got activity on it. You see going high and low, so it's got activity. I'm getting a stable signature address 1, but it's not actually writing into the memory. So I need to look at on the schematic here. Let's see here. Moving the camera around, rotate clockwise. Here's my RAM. Is pin 3 the read write? Pin 3. See sheet 1 of 2. Oh God. I think it is. I'm just assuming. So whatever's controlling pin 3 for that read write, I think is jacked up. That's what I'm thinking. Alright, let me look at that and come back. Okay, sometimes I'm blind, but you can obviously see write enable right here. That's pin 3. So write enable comes over here. Rotate this clockwise, clockwise, clockwise. There we go. Okay, the write enable comes from right here, the 7432 at 4R. You can see write enable 1, write enable 2, write enable 3. Those for the 3 columns. That is partially driven from the 7604. Where's the read-write line? Read-write line comes from the CPU, and that's what we're controlling, into this buffer here. Or is that a multiplexer? 73, no, that's a buffer. So from pin 10 probably to pin 9. Pin 9 gets tied into address 15. No, it comes in by itself. Then over here comes into the 7404, which feeds the 7410, which feeds the write enable. So anyway, there's a lot to go through to see what the hell's going on there. But unfortunately, when I went to look and probe around, I lost my clock again. I was probing around on the board and I lost my clock. I came to 7P, checked my 12 megahertz, came up to 6R, did not have 6 megahertz, did not have 4 megahertz, came up to 7R, and this is jacked up. I got 12 megahertz coming in to the clock, and I got nothing coming out of this thing. So let me show you that real quick. Alright, so I was probing around and I realized that the way I knew I had no clock is my cat box all of a sudden CAT BOX FPGA said, hey, you have no clock anymore. And I'm like, oh, okay, what the heck? I'm checking all my connections and stuff because we had already replaced this chip and knowing it was good, or maybe it was this chip, I don't know, one of these 74s. So I immediately went to there. It wasn't those. I verified them, checked them with my tester, started probing around, and pin 12 is the 12 megahertz clock, and pin, that's to 1, that's like to the second output of this thing, and then the number 1 output is driven by a clock on pin 12. The second output is driven by pin 9, which is also 12 megahertz. But pin 1 and 2, no, pin 2, what is 1? 1J, I think that's like fed by something else, I think. And there's nothing on that. So really we're looking at 1K, which is pin 4, which I think is just tied high. If you can see it. Let me slow down my clock. Volts, seconds per division. Pin 4, 1, 1, 2, 3, 4. So that's high. If I put on my DC volts, we'll see it a little bit easier. 1, 2, 3, 4. We have 5 volts. And basically on the outputs are pin 2 and 3. Pin 3 is really an output, and it's just hanging out at 0.25 volts. It's not really doing much of anything. Kind of just hanging there. Pin 3, 3.5 volts, and that's not connected to anything, so it's floating. So this 74LS107, which I probably don't have any, is jacked up. I'm gonna cut that out and replace it. It is close to here. It kind of does look, it has like a little bit of corrosion or something. I don't know if it had corrosion or not. Oh, does it feel hot? No. I don't know. Whatever. Got to replace it. I think that's bad. Okay, back at this. Replace 7R. Got a 74-107. It's not a 74LS107. Hopefully it's the same. No idea if it works. Have not tested it. I don't even have the CPU in. Just going to power up. And we get some weird stuff on the screen there. But let's go ahead and check 7R pin 3. 1, 2, 3. We got 4 megahertz. Adjust my seconds per division. So yeah, that was the problem of not having clock. There we go, 4 megahertz. I still need to adjust my thing. It's pretty fast, 4 meg. There we go. And then if we go to pin 6, that's pin 3, 4, 5, 6. 4 megahertz there as well. And then we can go right to our 1 megahertz, 7L, pin 5 and 6, 7L, pin 6 there's our 1 megahertz again. So gonna hook up the CAT box again, and we need to try to figure out what's going on with our read-write lines, right? That's where we left off. If I got my CAT box up and running again. There is my signature analysis. I loaded my decoder Prom. Let's see here if we reset. Okay, we're going to start with pin 8. This tool is so cool, and anything that you are testing that is really driven by the address bus, the signature analysis part is really nice. I mean, it does get a little bit more complicated when you start wanting to do the video counters and stuff like that, and moving clocks and start stops around. But Fred has made it so easy that you don't even have to worry about your clock and start. It's all done internally to the system. He's disabling the watchdog. I don't even have the watchdog disabled manually like I did. We're going to come to pin 8. 1, 2, 3, 4, 5, 6, 7, 8. I assume these are the outputs. that pin 8? Okay, pin 9.
Pin 10.
And then it's just telling you, I know he's done this, but then it's telling you what pin to go to next.
Pin 11.
If I can hold it.
Pin 13.
And then we come to pin 13.
Pin 14.
And this is basically checking all the outputs.
Pin 15.
I don't have to have a signature
Pin 16.
document.
Pin 17.
Or anything.
Pin 23.
Pin 23.
Test complete.
And then it says test complete. I don't even have to do, I mean, that's just crazy. And this address decoder partially controls the write enables there. And we could check the buffers. I don't know. Will it let me just do it if, no, let me figure that out. But I could check the buffers and stuff like that. I'm going to do that, but I'm going to check more things on the address line. I just wanted to show what it was like doing this one, because that's just cool. I mean, it's just so freaking easy and simple to do that. Alright, again, knowing what tool to use and when, I broke out my logic comparator. I'm going to show you on the schematic in a second. But basically, I wasn't making any progress with the read-write line, being able to, you know, read these RAMs, and changing the read-write having an impact on pin 3. So let me look at what I did, and I know I didn't film it because sometimes I'm lazy. I don't want to film. But I did the read-write line, followed that out, came to that buffer that I talked about before. Where am I at? 2K. Oh yeah, right here, 2K. And every time I press read-write, I could see it changing on the opposite side. So it changed pin 10. If I toggled that read-write, it would be, you know, 10 would change, then that would make 9 change. Then that came into the 7404. Pin 1 would change, pin 2 would change. If I toggle back and forth, these are like inverters, I'm pretty sure. This is a buffer, and then this is an inverter, I think, right? 7404, I think so. I looked at the 7410. The write enable does have activity, so the inputs have activity, and I think the output is having activity too. I don't know if I checked that actually. But regardless, then I came over here, because the write enables are partially fed from the 7410 as well as from 4K, which is driven by the address decoder, as well as, or the pseudo address decoder, as well as address line 14 and 15 through 4J. Is that an OR or something? I don't know all these symbols off the top of my head, but what would that be? It doesn't really say. Anyway, I do get a stable signature here, but this is not in the signature analysis. So this is an occasion where somebody needs to document the signature. So I do want to go and do that and help contribute to the FPGA CAT box. And I do want to document the signatures from 4K, because if you're testing 3K, you might as well come here and test the outputs with signature analysis of 4K. That way you can verify that part of E1 and WE are all good. But that is not in the signature analysis file, and I'm going to add it in a second by putting in my good working board. But anyway, the ones I highlighted in yellow, I use I used my logic comparator because I couldn't use signature analysis for those. So you know, I didn't have any signatures, therefore I broke out the logic comparator, and both of these chips tested fine. That kind of points me to the 7410 or the write enable line that is being generated down by the RAM chips on a second sheet. So this WE could be bad. We know E is good, and we know this is likely working as well, because that's just like what is that? An inverter, I think, right? And so every time I hit read write, that's changing. I just don't know if that output is correct or not. So logic comparator on the 7410 is a good idea. as well. So I'll do that and also check, generate some signatures too. Okay, it's probably been a week. I'm back at this, and I was looking at the wrong row. So I still might come back and do some signatures and stuff, but this is the row that I should have been looking at for pin 3. I don't know why that didn't dawn on me, but this is row 1. This is write enable pin 1, write enable pin 2, write enable line 3. WE1, WE, this row here, WE2, WE3, and if I go ahead and let me go ahead and load it again. Signature analysis, load, Defender Bank 1 test, and it says, you know, make sure pin 2 is low. Check on pin 2 and pin 3. So that's what we're going to do, but it should be this one right here. This is pin 2. You can see that's A0 and pin 3, and it's low like it should be. And so yeah, that's pin 2. There we go. Address 1. So I'm checking pin 2 of everything in the row. 2, 3, 4, 5, 6, 7. Okay, so that should be writing data into that memory, and then if I uncheck that, pin 3 should be high, and it is. And if I check pin 14, 1, 2, 3, 4, 5, 6, 7, 8. This is pin 14. Alright, I'm not getting data out is not what data in is. I should read A0. What? That's weird. 9, 10, 11, 12, 13, 14. Okay. Basically, I'm just coming in here and I'm probing pin 14. 05 CF, that's not right. That definitely doesn't look right. It just looks high on the data output line. Okay. We got some data output lines high. It's a different chip. Different chip. Oh boy. Alright, so let me see. I don't know why these are high. Let me check with my oscilloscope. Like, some of these are high. That's what that output looks like. I don't know what. Well, that looks low. Something weird going on there. Should be taut. That looks like data to me. I'm looking at all the outputs on those lines there. They don't look I don't know if they look good or not. The signature analysis shows them as high, but that looks like normal data coming out. Let me go back to my signature analysis. I might need to adjust my probe timing or something. Maybe I'm not able to get my probe timing correct. Or now I'm getting actually some, at least I'm getting a signature, but it's not known. Okay, so yeah, I'm getting signatures on all of them. The data lines aren't tied high. It's just, you know, probably some corrosion on those RAM chip legs and stuff. I'm getting signatures on the data output line, but they're not correct. So that means the data going in, the data coming out, or the data going in, even though it reads correctly, I'm thinking the row select and column select is jacked. That's my best guess. Alright, I put my working board back in. I'm not going to actually film anything. Well, I'm going to film, whatever. I did take some signatures off of the pseudo address bus and trying to get down to the enable pins, especially like E1, E2, E3. And I also took a frequency measurement of the row address select and column address select, I guess. But what we didn't look at, and what I was thinking is the data coming in, I don't know, we didn't check the data buffer enable pins, which are these 74 LS3 74s, I think. There's this one, and this one. I think this one controls this bank, this one controls this bank, and this one controls this bank. I'm not sure about that. But we need to check the enables, these E's right here. And just because I had data coming out, because it was being addressed and the ROM was enabled to send data out, doesn't mean that it was getting switched back to the CPU, or that these buffers are being enabled correctly so that data is coming into the chip that we're writing. So we can actually check our data bus counters probably at these 74LS374s, I think is what they are. So that's what I'm going to do. I'm going to put the original board back in, and we're going to do our data counters, and we're going to check to make sure the data counters are coming through these buffers and getting to the actual RAM chip probably. Yeah. Okay, I'm trying to think of the best way to describe this. So the FPGA CAT box has a data bus counter. So it's basically doing the same thing as it's doing on the address bus, it's doing on the data bus. And this over here on this side of this buffer, or whatever it is, is it bidirectional or something like that? 74L, whatever. But anyway, so what data, if I'm writing to the RAM, then what I see on pin 16, I should see on pin 17. What I see on pin 19, I should see on pin 18. If you can see that okay. Right there. And then when I'm reading, that's going to come out pin 14. And as long as it got into the RAM and addressed correctly, it should come out the same way, but it's not coming out the same way. So we can verify if these are working at least by, let me just do it. I'll show you. We have our bank 1 test set up. We are going to write, and we're going to take our logic probe, and we're going to come to pin 1 of the buffer, and I'm saying it's a buffer. I think it is, but the LS, no, that's the wrong one. That one right there, 374, and it is high. Is that right? Is that supposed to be high? when I'm writing to it. Let me see, I'm double click it, go back to pin 1. Okay, yeah, so it's supposed to be high when I'm writing. And then we're going to come to, let's do pin 9. And you can see I have A7, which is correct. That's the, or it's data line 7, but it's reading the same as the address counters. Alright, let me hold that. What's the other side of 7? So that's going to the RAM chip. Pin 6 is the corresponding. Now I'm screwed up now. We did pin 9. Pin 9 is data line 7. Pin 9 and pin 8. So alright, pin 9 and pin 8. That's pin 9. Okay. That's pin 8. That doesn't make sense, right? Pin 9. And then pin 8. Okay, let's look at this real quick here. So here from our MPU data bus, pin 9, data 7, data line 7, should go to pin 8 when it's in write mode, and there's junk data going on that. And why is that? What else? Is there something else? That's interesting. I think that's, I gotta think about that, but I think that's probably our problem. I almost want to run this test on my working board now, because coming from this direction. Yeah. Alright, never mind. I looked at it a little more closely. So the on this side of the, I think it is a transparent latch, or edge triggered flip-flop or something like that. But anyway, it's like a bus driver, I guess. And whatever's on this side is coming from the MPU, but the MPU is also directly putting data into the data in of the RAM chips. So it's only data coming out of the RAM that needs to be, latched over onto the MPU data bus. So stuff coming from this side, once we're reading it out of here, then needs to come on this side. So the fact that the data coming out is not accurate has to be something on the address bus. And this is it says memory address bus, so it has to be on this side, which could be, well, we know the address bus is probably okay, but if these, I forget what these are called, these LS153s, let me look that up real quick. Yeah, they are multiplexers. So, and I've done this from a signature analysis standpoint on the other Joust and stuff like that, but if these aren't working correctly, you're going to get jacked up addressing because you have 4 buses that it's trying to multiplex into 2. So I don't know, I'm totally guessing. I did check the row address select and the column address select, whatever that is, CAS and RAS, and those look fine. So bad data going in, but we know the data counters are working because we see that as on all these pin 2s, that looks good, but it's not getting put into this RAM correctly, so that when it comes out it's junk, and that has to be due to the address busing. Alright, because I didn't want to mess with the signature analyzer, I'm still running the data counters and the address counters, and I started probing the multiplexers, the 153s, and it's there. It's 4F, 4H, 3G, and 3I, I think. And the only one that reads bad is this one at 3G. So let me get a scope on it real quick, see if any of the pins are jacked up. I might want to troubleshoot it further. I don't know. Is the logic comparator enough? I think it is. I might just remove it. We're going to look at the outputs. So we could have probably done this a little bit easier, but let's look at the outputs of these multiplexers. This is a working one, pin 9. No, that's a non-working one. This is a working one, pin 9. You can see that. And this is my non-working one, pin 9. That is not good. Here's another working one, pin 9, and it's only 2 outputs. I think. Why isn't that one working? Interesting. That should probably look better than that. That one looks good. Why does this one look like shit? That's a different one. That's 4H. Let's check pin 7. That looks good. Pin 7, that looks good. That looks bad. That looks bad. That's pin 7 of 3G. I don't know. This one, pin 9. Oh, you know what? I don't think that's tied to anything. I'll double check the schematic on 4H. 4H pin 9 is not tied to anything. That's why it looked messed up. So we definitely have a problem at 3G. That multiplexer, I'll replace that. Alright, I actually cut out the wrong chip to start with. I cut out what is that? F or something. Replaced that one. Realized I made a mistake. Then I cut out 3G. Replaced that one. I think I'm just going to go straight to load config Williams Defender new, open. Let's go to our RAM, start RAM test. Oh, we still have a failure. We're not able to read the RAM. Alright. Oh my god. Signature analysis, load. Defender RAM test. Oh boy. Let me see here. Go that to low. Pin 2 is A0. That's low. Come to high, go to pin 14. We have A0. Let's go to pin 14 of the second chip. A1. Okay, that's good. Okay, so I'm reading, now we're getting data in and out here, which is good. The data we're getting in is the data we're getting out, at least on this first bank. A4, A5, A6, A7, okay. So we know, sorry, I'm moving the camera around. So we're able to do our signature analysis on this RAM. Data going in, data coming out is fine. Is it making it all the way to the CPU? No, or at least I don't think so yet. So I'll come back. I'm just going to run this test for all the other banks, and then we'll see. So I was probing around and using the data bit counter, the data bus counter of the FPGA, and just trying to check, the behavior of these 374s, and then I came to this this buffer. I think it's a 245 bidirectional buffer, I believe, going to the CPU data bus, and I haven't probed all the lines yet or not, but I ran the RAM test. And this time what I did is I just disabled all of them except for one row. Actually, let me run it, see what it looks like when I do it this way. Because I'm getting some data bits that are failing. Okay, that's interesting. Let me disable that, see if I get the results the same. Start RAM test. Three was good, 5 was good, and 6 was good. 3. See if I repeat that. What is that telling me? Sometimes these two data bits read correctly, but it's either a 1 or a 0 because I'm writing FF. Maybe let me abort that. Random. Alright, well, never mind. I thought I was onto something, but I don't think so. I think it was just lucky because whatever was written in there was a 0 and it happened to read it back out as a 0 or an F or something. Alright, so scratch that. That doesn't make any sense. Pin 5 worked that time. Data line 5. And data line 5 doesn't work. So I think it's just kind of random. There's not like a specific data line that's tied high or low. Alright, scratch that theory.